or I don't know. All right, so let's begin. First things first, can you guys see well? Do you want me to zoom in more? Let's get the nice, perfect. All right, so we're beginning on chapter titled Energetics, whatever number it is. And they're ordered in the number. I don't know if these additions change. I don't really know. I think they're the same. So whatever chapter this is number 1. I've written most of them down in case you don't have the book. The only thing that I'm missing are on some of the ones that are problem solving. I didn't write the A, B, and C and the answers because it's solving. We'll get to the answer once we solve it. But the ones that are like concept-wise, and then I wrote that down. So, all right, the first thing is, when you have a 45-gram sample of an alloy at 100, oh, can everyone see? Yes? We're good? I'm going to take that as a yes. Right. When a 45-gram sample of an alloy at 100 degrees Celsius is dropped into 100 grams of water at 25 degrees Celsius, the final temperature is 37 degrees Celsius. What is the specific heat of the alloy? All right, so a quick tidbit on thermodynamic and what you guys have covered so far. If you're talking about a change of temperature as related to energy in form of heat, you are likely going to be using the equation mc delta T. For all intents and purposes, you guys don't have any other equation that you can use that relates temperature change to energetics. Solely those two. If you are not relating a temperature change, let's say you're going through a phase change and they specifically use the words condensation, evaporation, fusion, melting, freezing, those things that signify that I am changing state, then you'll be using Q equals the N, so the number of moles times your delta H of vaporization if you're vaporizing or condensing, or fusion if you are melting or freezing. But since this one perfectly states we have two different things, both are changing temperature, I know that I'm going to be using Q equals mc delta T. So a little nice thing about being able to eliminate answers, I'm not going to eliminate them right away because there's still a possibility that they could be right, but chances are my last two aren't going to be right. One of the things that makes water really, the most abundant thing and why we have life is because it has a high specific heat capacity. So chances are that my alloy isn't going to be higher than water, but I'm not going to eliminate it right away. That's just if you guys find yourself short on time and you guys can't solve the problem, that'll be a nice way of leaving it at 50-50. It's more than likely going to be something less than the specific heat of water. All right, so here's where I wrote that. Yeah, whenever you're talking about a temperature change, you're going to be using Q equals mc delta T. Pay attention to your units. I have two here written, and the only reason being is because specific heat is either in joules per grams degrees Celsius or in joules per mole. So if you're in mole, then it's not going to be M, it's going to be N. And they can also change it to Kelvin at the bottom as well. There's a lot of different ways to measure heat. All right, so what is happening in this problem is I put the alloy into the water. The alloy is at a higher temperature than water, so it's going to transfer its energy to water, and it's going to raise the temperature of water as the temperature of the alloy drops till they eventually reach a common temperature. So I'm going to plug in everything I have for water. So the amount of energy to change the water is, I have 100 grams of water, the specific heat of water, and the temperature change of water. I'm going to solve for that. Once I do, I can plug in the joules back into the alloy so I can solve for its specific heat because they gave me the amount of alloy that I had and they gave me the temperature change of the alloy. The only thing they didn't give me is energy, but I was able to find the energy with water, or the temperature change that water had. When I plug it back in, solve, and your answer is 1.77. Any questions? So that's the whole problem. Any questions? I can move forward? All right, you're the only person reacting, so whatever you say just goes, okay? All right, now we are on to number 2. When 68 grams of energy are added to a sample of gallium that is initially at 25 degrees Celsius, the temperature rises to 38. What is the volume of the sample? So what equation do you guys think you're going to be using, judging by what they're asking you? Oh, awesome, over there in the back. Yeah, Q equals MC delta T, or MC delta T. You have this amount, we don't know yet, we know volume of sample that is initially at 25 degrees Celsius. It changes to 38 after you put this energy into it. So I'm putting in energy and I'm getting a temperature change. I know that I'm going to be using Q equals MC delta T. Now the tricky part is finding the volume. Density is, for all intents and purposes, a conversion factor between your mass and your volume of a sample. So if they're ever asking you for volume and you know that the equation has mass, they're probably giving you the density so that you can solve for it. So my plan of action is to use Q equals MC delta T to solve for mass in grams, and then I can use the density of gallium to find the volume. Questions? Okay, moving right along. All right, so calculate delta H for the following reaction, and you're given bond energies. And most of the time when they ask you to calculate the delta H for an overall reaction, you can find it in many ways. If they give you the bond energy, you can find it. Sometimes they give you the heat of combustion. Sometimes they give you the heat of fusion for each molecule. And I doubt that they will do this, but if they give you the actual heat products, when you add them together and then you do products minus reactants, at that point it'd probably be heat of fusion. For in this case, they gave us bond energies. So in order to use bond energy, since bond energy is the amount of energy required to break the bond apart or released when it's formed, I'm going to need to draw my bonds. So I drew my molecules, or my individual ones. And I'm going to tell you one thing, for when you're talking, when it comes to thermo, the only thing that the sign tells you is whether energy is leaving the system or entering the system. Because when it comes to thermodynamics, if you're going in the forward reaction is positive, and the reverse is going to be negative. So for example, if it takes 159 joules of energy to make a fluorine-fluorine bond, to break a fluorine-fluorine bond, it's going to release 159 kilojoules of energy if you make it. So ignore your signs that are given as constants when it comes to bond energies. And if you are a product, then you're going to release energy because you're going to make those bonds, make it negative. If you are a reactant, you are requiring that energy to break those bonds, make it positive, add everything together. Okay, so yeah, I think I wrote it there. Any questions? Don't be shy. Okie dokie. It's a lot quicker for me, right? All right, so number 7, more heat is derived from cooling 1 gram of steam at 100 degrees Celsius to water at 50 degrees Celsius than from cooling 1 gram of liquid at 100 degrees Celsius to 50 degrees Celsius. And the reason being, and I'm gonna let you guys do this one, since it's a concept question. What do you guys think? Tick tock. Tick tock. E. Oh my gosh. Oh, you're gonna do so well. Or did you say D? E? I'm still hearing E. Or just random letter. J! Okay. Yeah, beautiful. D. D as in dog. And I did out the math for this one just because I've always liked these questions, and they have one in your book where it's like calculate the entire energy from condensing all the way from steam to water. No? Okay. So before you begin cooling, and this is the equation that I said, if you're talking about a phase change, you're going to be using. So before you even begin cooling the steam, you're going to have to change it, yes. D, as in dog. Oh, what it said? You have to use the heat of condensation. Actually, for this one's a really good one where it comes to process of elimination. The steam is hotter than water. It literally says they're both at the same temperature. Like they're both at 100 degrees. So the steam occupies a greater volume than water. I'm going to keep that one just because like, might as well. Like it could be, you know, steam is a gas. It could be at a greater volume, even though you can probably have them at the same volume as well. The density of water is greater than that of steam. There is no, density is related to size and volume, not to heat or energy in any way. So I would remove density, which leaves me at 50-50. Flip a coin if you're stuck between these two. Even though I would still eliminate the volume one because it's just weird. Like what does volume have to do with energy? Unless you're talking about like the volume and pressure. All right, so yeah, you still have to deal with condensing the water. And when you have a phase change, you're going to use Q equals N delta H of vaporization, or fusion if you're going from liquid to, from solid to liquid or liquid to solid. Plug in everything that was given, and then you can cool the water. And your cooling of water is going to be Q equals MC delta T. Plug in everything that was given, and that is a mathematical representation of why D is the answer. Any questions? Yes. What does what actually mean? Even though you have water and steam, they're both at 100 degrees Celsius, and they're cooling to the same temperature. So if you were to use Q equals MC delta T to solve for it, you would get the same amount of energy, but that's not the case. When you cool steam to 50 degrees Celsius, you actually require more energy or release more energy than when you cool water. And the reason being is because you have to release energy. You're going to release a lot of energy. Actually, if you compare the energies for change of phase, you release 2.26 kilojoules. And for change of temperature, you release 0.2 kilojoules. So you end up releasing a lot more energy just to get that steam to water, and then you have to cool that water. Does that make sense? Any other questions? All right, so this is another bond energy one. They asked me to calculate the delta H, and they gave me the reaction, and they gave me the bond energies. Again, when given the bond energies, we're going to draw out our molecule, and each bond there, and that's up to you guys to remember how your molecule is drawn. And then we're going to assign for any of the reactants, since they are breaking down, they're going to require energy to break those bonds, so you're going to make all of those bond energies positive. If you're a product, you're going to release that energy as you form those bonds, so you're going to make them all negative, and then you're going to add all your bond energies together. However, the reason why I picked this one, it's not like the other one. In this one, if you look at it, the only bonds that are changing are the ones in blue. The ones in purple are not, and can you tell the difference between purple and blue? I'll circle the purple. So the ones in purple are not changing. The only ones that are changing are those in blue. So I can ignore. If a bond is not changing, it's not reacting. It's there in the beginning and it's there in the end. Nothing happened to that bond. I'm going to ignore it for adding purposes. I'm only going to work with the ones that have been modified in any way, shape, or form. So the reactants, I have one NH bond, and it's a reactant, so I'm just going to keep it positive. I have a chlorine-chlorine bond, also a reactant, keep it positive. Then I have this nitrogen-chlorine bond forming, and as it forms, it's going to release energy, so I'm going to make it negative. And then I have this hydrogen-chlorine bond also forming, so it's going to release energy, I'm going to make it negative. And then I'm just going to add everything together. Any questions? Yes. Yeah, because if I add I know that I have two other NH bonds on both ends, but if you add them on one side and subtract them on the other, they're just going to cancel out. So those circled bonds, I'm just going to ignore. They didn't change. Even if I broke them all, I reformed them again. So the amount of energy that I put in to break them, I just made it again. So there's no need to include it in my math. It's just going to make it tedious work. Only worry about those bonds that are changing throughout the reaction. Any other questions? All right, so I wanted to bring this one in because they're giving you heat of combustion instead. And I'm going over so many of these because last semester I had a lot of questions, so I figured to cover a couple more. So for heat of combustion, or enthalpy of combustion, enthalpy is heat, entropy is delta S. Gibbs free energy is delta G. All right, when enthalpy of combustion is given, that is the amount of, it's always going to be negative because enthalpy of combustion is the amount of energy. I'm sorry, it'll be positive, yeah. Okay, so never mind. The sign won't matter again. So when given enthalpy of combustion, that is the amount of energy released or required when you break down that compound. So if you're forming the compound, flip the sign. And you're forming compounds if they are products. If you're breaking down the compound, keep the sign. If you're given enthalpy of formation, so delta H of formation, that is the amount of energy required or released when you form the compound. So if you break the compound down, and it's a product, a reactant, and you're breaking it down, flip the sign. If you're making it, keep the sign. So in this case, it's combustion. So it's amount of energy released when it's broken down. So I'm going to keep the sign for the reactants. And I'm going to flip the sign. Did I say that right? Yeah. And I'm going to flip the sign for the products. Then I'm going to add it together. And you get an answer. Does this make sense? Any questions? Yes. For formation? Okay, it just depends. Like when they ask you to find the overall delta H of a reaction, they sometimes give you bond energies, and so we already went how to do those. Sometimes they give you delta H of combustion, and sometimes they give you delta H of formation. So it's just if you ignore the sign, the number's what really matters. But now we're going to ignore the sign until we assign our own signs. Does that make sense? So don't get twisted with that. So if it's enthalpy of combustion, ignore your signs. But we know that combustion is the amount of energy released when you break something down. So if it's being broken down, keep the sign that it's given. And the things that are broken down are reactants. However, if it's being formed, that's the opposite. So we're going to flip the sign. And everything being formed is a product. Products are formed, reactants are broken down. If it's formation, however, then it's the other way around. That is the amount of energy required to form, the amount of energy required or released to form the compound. So we're going to keep the sign if the compound's being formed, thus if it's a product, and we're going to flip the sign if the compound's being broken down, so if it's a reactant. I can move forward? Yes? Any questions? We're all good? All right, so this is number 16. Again, if you want to follow through in the ACS book, I recommend you do that. I've written all of them down, but you can also look at the ones that I've skipped and circle ones that you've had issues with. If I have time in the end, I will more than gladly go over it. All right, so given these values of delta H for each of the reactions, what is the value of the overall reaction? So in this case, we're going to have to manipulate each, it's a chapter on energetics. We're going to have to manipulate each of these elementary steps, mechanism steps, in order to get the overall reaction. Once we add them together, I want to have that as my overall reaction. So the first thing I would look at, I would first find if any reactions need to be reversed. And a really good way to look at it is, if I look at my overall reaction for H2O2, I have an equation for that, equation number 2, that'll generate hydrogen peroxide. But hydrogen peroxide is a reactant, but in this one is a product, which means I know I'm going to have to reverse equation 2, so that when I add it, it'll be as a product. If you reverse an equation, you just change the sign. And that also goes for delta S, delta G, and E of cell. If you reverse a redox reaction, a half reaction for redox, if you reverse it, you're just going to get the opposite E of cell. So that works for delta G, delta H, and your E of cell. If you reverse a reaction, you just reverse the sign. So in this case, reaction number 2 was reversed. Change the sign from negative to positive. All right, the next thing you would ask yourself is, do any reactions need to be multiplied by a factor? If you multiply by that factor, multiply your delta H by that factor as well. And in this case, I know that I need to multiply equation 2 and 3 by 6. And an easy way to tell is I have 6 hydrogen peroxide. Hydrogen peroxide can only come from equation number 2. So I'm obviously going to make this one 3 times over. And then once you have finished doing this, add them all together. Double check and make sure that you have the overall equation. If you have the overall equation, then you can just add all of your delta H's together. Any questions? Yes. K. For K, so for your Equilibria, or is it rate K? It's either rate K or Equilibria K. Probably Equilibria. No, definitely rate. Rate final answer. Because rate is the only other one where you have elementary steps that you manipulate. If you recall, when it says predict the rate constant, that's the one I think if you multiply by a factor, you raise it by the factor. If you reverse it, you inverse it. And if you add them together, you multiply. Okay. So in which process is entropy decrease? Entropy is heat. My bad. Entropy is delta S. Enthalpy is heat. Delta H. So the one with the H is delta H. The one without the H is delta S. All right, so when you have entropy, you guys are going to have to actually remember. For a decrease in entropy, do you go towards order or towards disorder? Towards order? Cool, thank you. All right, so you're going to go towards order. You're going to look for something that's more ordered, or you could look like one that's not like the other, because you're either going towards order or towards disorder. It's 50-50. If you find the one, like you don't remember, I'm like, oh, I don't remember entropy's decrease. Just pick the one that's not like the other. So dissolving sugar in water, are you going from order or disorder? Towards order or towards disorder? Disorder. If you have expanding a gas, are you going towards order or disorder? Evaporating a liquid, towards order or disorder? And then the last one's towards order. By default, it's the only one that's not like the others. Even if I forgot, that has to be the answer. Awesome, you guys are great. Hey. When a liquid evaporates, which is true about the signs of the enthalpy and entropy changes? Well, we already decided I would do entropy first, because entropy is easy if a liquid evaporates. If you're going from a liquid to a gas, is your delta S going to be positive or negative? All right, come on, guys, positive or negative? All right, so you're going to remove all the negatives? Yes. So at that point, it's 50-50. But let's think about our delta H equation. And let's go back to when we were talking about energetics. When we're trying to evaporate something, are we putting energy or heat into it, or is heat being released once you evaporate? Yeah. You're going to have to put energy into it so that you can get those molecules all hyped up and they can break apart. So it's going to be positive. So the answer is A. All right, so a particular reaction has a negative delta H and a negative delta S. Which statement is true? All right, so for this one, I want to draw a nice little chart. And we're going to go through it in case you ever forget. For spontaneity, all of these are dealing with spontaneity and temperature. The only reaction that you know, and 9 times out of 10, if they're asking you this question, it's the reaction you're going to use. All right, delta G equals delta H minus T delta S. If you go all the way down and you use each of the signs, remember that delta G, if it's positive, you're non-spontaneous, and if it's negative, you are spontaneous. So positive, you're not going to go forward, and negative, you are. So let's make delta H positive and delta S positive. Well, in order to get delta G to be negative, you need that delta S to be large enough so that when you subtract it, you get a negative number. So you're going to want temperature to be high. So this guy's spontaneous at high temperatures. If you keep delta H positive and delta S negative, well, a negative times a negative makes a positive. You're always going to be adding to this. It's going to be non-spontaneous at all temperatures. Does that make sense? I kind of went through that really quickly. If you make delta H negative, and to it you're subtracting, and delta S is already positive, you're subtracting to something that's already negative. You're just going to make it more negative. It's going to be spontaneous at all temperatures. And the last one is negative and negative. If you add a negative minus a negative, so that negative minus a negative delta S is going to be positive. So in order to keep this negative, you want that second half of the equation to be really, really small. So you're going to want the temperature to stay really, really low so that you're adding a small number and you can, in hopes, still keep it negative. So this would be spontaneous at low temperatures. And if you ever get stuck, you can always think your way through this, hopefully. Unless you're like really tired and you're just like, oh, I can't think anymore. Any questions? All right, cool. That concludes the chapter on energetics. Any questions? Any specific problems if you brought your book that you would like me to try and attempt? Please don't make me do math, but if I must, give you guys 5 minutes. Actually, no, what time is it? I finished at what, 10:30? I should be done by 10 if it took me 30 minutes, which leaves 30 minutes of actual real questions. No questions? All right, cool, moving right along. Oh, now you have a question. Yeah, what's up? Is it a specific number?
No, it's actually from the ATS.
The one that I'm hopefully using? Okay. Okay, yeah. What number is it? Page and number. All right, if you are changing, at that point I would say you're at Equilibria. Yeah, you're at Equilibria. Because your reaction, if you're going forward, you're going to release energy. But if you're not releasing energy, that means that the reverse and the forward reaction are happening at equal amounts. You're releasing and you're going back and forth, so you're adding them together at equal amounts. And so they're negating each other, the positive and the negative, so you're at Equilibria. Anything else? You guys are so alive. All right, so this brings me to dynamics. And beautiful, beautiful subject it is, dynamics. All right, so in the gas phase reaction, A2 plus B2 to 2AB, proceeds by bimolecular collisions between A2 and B2 molecules. If the concentrations of both A and B, A2 and B2 are doubled, but by what factor will the reaction change, or the speed of the reaction change? For rate, actually I can't say that, that's not a fall fact. I can say, okay, for rate, most of the time, you're only gonna be dealing with the reactants. Most of the time, you don't really deal that much with the products. And that's just for most, like there is that one. All right, so for a bimolecular process, your overall rate order is going to be 2. So if you have one molecule, then that means that one molecule is going to be raised to the 2. If you have 2 molecules, each of them are going to be raised to the 1, so that your overall rate order is 2. For a unimolecular reaction, your overall rate order is 1. So either you have 1 and 0 and 1 and 1, which in turn ends up being just the other one at 1. Or you have just one molecule with a rate order of 1. All right, so if you plug in the amount by which you are doubling, if you're tripling or doubling or whatever, by the amount by which you're multiplying as your concentration, and you just follow it right all the way through, ignoring your K, you'll get your answer. It's times 4. So this one's going to be going 4 times as fast. And this will work for pretty much any of them. Just plug into your concentration whatever your multiplication factors by. So if they say I tripled one and doubled the other, then it would be 3 times 2, 6. Any questions? All right, so for the reaction of chlorine and nitric oxide, doubling the concentration of chlorine doubles the rate of the reaction. So what is the order of chlorine? I heard, oh, okay, first order, cool. So we automatically already know that chlorine is first order. So whatever they're asking me, I'm just going to ignore anything that says first order for chlorine as of now, even before I finish. Actually, well, the rate of the, yeah, I'm just going to ignore it because it's wrong. So that one's wrong. So at that point, we have it to 50-50. If you don't know what to do, flip a coin, eeny, meeny, miny, mo, whatever you feel most comfortable with. But for those of us who do know what we're doing, not me, I mean you guys, I just pretend really well. If we're going to work with the nitric oxide. So for the rest of the question is, doubling the concentration of both reactions increases the rate of the reaction by a factor of 8. So for the previous problem, I plugged in the doubling factors, or whatever factor I multiplied by, into my concentration. And they already gave me the order, so I solved for rate. In this one, they're giving me the rate, and I'm solving for order. But it works for the same way, and you can just neglect your x for all intents and purposes, because your k, not x, sorry. And we can plug in, we know that chlorine is first order, so we plugged in the first order for chlorine, and it was doubled in the second part of the question. They were both doubled. We're trying to find the order for nitric oxide, but its concentration was doubled. And when this doubling occurred, your rate went up by 8. So if we solve for the order, math. And we get our rate order for the last one equals 2, which leaves us with my answer being B. Right. Yes. Ah, snap. My bad. So it's first order for chlorine. I would have canceled out second order and second order, and it would have left me. It's just everything. It still makes sort of sense, right? It's just my mistake. I'm sorry. Why didn't you guys tell me this before? You guys just let me talk and talk and talk. And it was just like, everyone was like, she has no idea what she's talking about. Or the worst, like, I've had it all wrong this semester. No. Don't leave with the wrong answer. All right. So, under certain conditions, the average rate of appearance of oxygen gas in the reaction is 1.2 times 10 to negative 3 atmospheres per second. What is the average rate expressed in atmospheres per second for the disappearance of O2? O3. All right, so actually I want to go down here first. This is how you can relate your overall rate law to your change in concentrations. They're not the same. And a lot of people get really confused with that when they're talking about rate of change and overall rate and your change in concentrations. In order for your change of concentrations to equal your rate, you're going to have to multiply it by certain factors. So whatever the coefficient, you put it on the denominator. And since rate of change is final minus initial, if you're a reactant, your final is going to be less than your initial, so it's going to be negative. But there's no such thing as a negative rate. And so you account for the reactants their change over time being negative by making that negative. Since this equation is talking about average rate of change in concentration, and I know that because they said, well, average rate of change in the disappearance and appearance, so that's the concentration. I know that I'm going to be using the deltas. So I'm going to write my overall equations for both of them as related to each other. And I can set them equal to each other because once I multiply both of their changes in concentration by their appropriate designated number, I'm going to ignore negative signs because negative is just to make sure that your rate stays positive. Once I set them equal to each other and multiply by their factors, their rates should equal each other, so I can do that. Does that make sense? And then a lot of people would like to plug this whole number in for O2. You plug it in only for the change because that only told you the change. It did not tell you the rate. And it takes a lot of reading into the problem to not get confused as to whether they're giving you the rate of the reaction or the rate and change of the product or the rate and change of its concentration. So the key words for this one, it said disappearing and appearing. I know they're talking about the change in concentration and not the overall rate. So once I solve for change of O3 over time, I get an answer. And that answer should be some answer on there, hopefully, unless I'm wrong, which is a possibility. All right, the activity of a radioisotope is 3,000 counts per minute at one time and 2,736 counts per minute 48 hours later. What is the half-life of the radioisotope? This also goes into account for when you do the nuclear chemistry, although I saw that this book doesn't have a chapter on nuclear chemistry, so maybe the only thing they care about is radioactive decay. I don't know. Or maybe I just didn't read the table of contents properly. That could also be a thing. When it comes to radioactive decay, since it's first order, your half-life, they either give you their half-life or they give you the K, or they give you everything you can plug in to find the K. That doesn't make any sense. I'm just going to move forward. All right, so they asked me to find the half-life. ln of 2 is equal to that 0.692 thing that you guys always go for, or that you tend to memorize instead of just ln of 2. And in order to find K, I'm going to use my integrated rate law. I know that I'm going to use my integrated rate law because they gave me a time and they gave me two separate concentrations. And if you're talking about rate and they give you a time and two separate concentrations, you're using your integrated rate law as opposed to your overall rate law, which only has one concentration at one point in time. It's only rate equals K times whatever your reactants are. There is no two of them. All right, so I plug and chug and solve and yay. Once I get my K from that, I plug it back into my half-life, and I get an answer. Questions? Yes. Any other questions? Okay. All right, so when the reaction was studied, the tabulated data were obtained. Based on these data, what are the orders of the reaction? So the first thing you're going to do is you're going to pick one, we're going to write our overall rate law. That's the first thing we're going to do. And to find whichever number, or whichever, if you're going to find n or you're going to find m, pick one where one is changing and the other is not. So in this case, I'm going to pick experiments 2 and 3. In 2 and 3, we have the concentration of H2O changing, but the concentration of CH3Cl isn't. And then what you're going to do is you're going to put your rate 2 over rate 1 equals K. Actually, whatever, already here. You plug them back in and you put rate 2 over rate 1. So this is my second data point. I plug in everything for it, and then I divide it by my first one. Since your K's are the same, they cancel out. And since the concentration for CH3Cl also stayed the same, well, if I raise an M also stays the same. If I'm raising the same number by the same number, I get the same number. So they're also going to cancel out. So I've effectively left it with just that. At this point, before you do any math, I'm going to suggest you plug everything in, so actually divide first. If you're one of those people that just go straight through, that's fine. But if you divide first, you might find that they did you really easy math. And you didn't have to do raising it to the whatever. We know that 2 to the what equals 4. Well, 2 to the 2. So we know that our answer for n is second order. And using this logic as well, you technically could have done this without ever having plugged it all in, which is the way I use in the second part. So in the second part, if I'm going to react from reactions 1 to 2, both of the reactants were doubled. Well, the first thing I'm going to do before I figure out, before I decide to do any math, if both of the reactants are doubled, then I can put them both under it and solve for it because I already have n. But before I do that, I'm just going to divide my one rate by the other and see if it's increasing by a solid number or an easy number, a factor of 2 would be easy, or actually any number that's just not a whole number. So at that point, it's increasing by 8, and it made my math really easy. Does that make sense? And you could have done this for this one as well, because this was also doubling from there to there. So you should have observed a doubling from here to a quadrupling, because it's second order. Yeah. Any other questions? Wake up. It's for your own benefit. All right, all of the changes increase the value of the rate constant for a reaction, except a decrease in the activation energy, raising the temperature, adding a catalyst, or increasing the concentration of the reactants. I like to work with equations. That's just the way that I am. And since this is talking about activation energy and temperature, I'm going to look at my Arrhenius equation. And keep in mind that if you raise e to a small number, you get a big number. Well, actually, that doesn't really matter for this equation. That's for the next one. My bad. So at that point, does the activation energy affect your K? It's in the equation. Yes, it does. Raising the temperature, also in the equation. So yes, it does affect it. And adding a catalyst, by definition, speeds up the rate of the reaction by lowering the activation energy. There's a definition of a catalyst. If you didn't know that and you got down to the last two, and you're like, oh God, what is a catalyst? Increasing the concentration of a reactant, 9 times out of 10, and I always say this because I don't like to give like 100% of the time, but it's a good model to go by. If they're talking about concentration change, that's equilibria. And equilibrium and rate are not necessarily 100%. Your concentration, your equilibrium and your rate aren't the same. So a change in concentration, it doesn't really affect the overall rate of the reaction. You can reach to it as is. So I would remove D just because when you're talking about a change in concentration, it's getting me into equilibria, which isn't the same thing as dynamics. Am I good? So the answer is D by default. All right, so this is another one where it's talking about the Arrhenius equation describes the relationship between the rate constant K and the energy of activation. And then it's giving you a series of scenarios and asking which of the following is true. And this is where it comes into account. Well, create, I can't get the... All right, this is where you take into account the fact that if you have a small e, e raised to a small number is a large number, and e raised to a large number is a small number. And your k, when you plug it back, is directly proportional to your rate. So if my k is decreasing, my rate is decreasing. If my k is increasing, my rate is increasing. So for the first one, at a constant temperature, so I'm going to eliminate temperature from the equation. I'm only going to be focused on activation energy, since temperature is always going to be the same. At a constant temperature, the reaction with the lower activation energies will proceed more rapidly. Well, if activation energy is on the top, that means decreasing it means that E is decreasing it. And if I raise E to a smaller number, I'm going to a larger number. So lower activation energies would, going to a smaller number, increase your K? Yeah, increase your K and then increase your rate as well. And actually at that point I'd be like, I'm done. That one's true. You can go through and check them all. So at a constant, well, if this one is true, then B cannot be true because it's the same thing. So at a constant temperature, the reaction with a lower activation energy isn't going to proceed less rapidly. So it's either more rapidly or less rapidly. You can't do both. So if you picked A to be correct, then B has to be false. So at a constant activation energy, a lower temperature in the bottom is going to make it an overall bigger number. An overall bigger number is going to be a larger number. Oh no, an overall bigger number. I think we got A backward. I'm sorry, I'm getting mixed up in my mouth. If a constant with, okay, yeah, at a smaller t would be, if you're decreasing the t, you're going to increase the number. If you increase the number, you're going to decrease your k, you're going to decrease your rate. Does that make sense? And then at a constant temperature, at a constant EA, well, with a smaller A value, you don't even have to work at this part. With a smaller, if you're decreasing the A, you're going to decrease your K because it's directly proportional. So even by default, we got to the right answer the first time, but you can check it all the way through. Are there any questions? I know I stumbled through this problem. So does anyone want me to go back and explain it? Is everyone okay with it? Are you guys here for Chem 2 as well? Okay, just like my voice? I'm just kidding. Right, so a catalyst changes the rate of a reaction by A, changing the mechanism, B, by definition, it decreases the activation energy. So we're just going to eliminate that one because it can't happen. C, increasing the concentration of one or more of the products. This is, again, we're talking about products, which is Equilibria, which is not, just because you go quicker or faster, you're ending at the same Equilibria. You're just getting there a faster way. Your rate only affects how quickly you get to your end. It doesn't affect your end point, which is thermal. Thermal is affected by the beginning and the end. Rate is just how quickly you get to the beginning, but it shouldn't affect the beginning or the end. So I'm going to eliminate C. And it decreases the relative energies of the reactants and products. If you're decreasing the relative energy of the reactants and products, again, you're talking about thermodynamic. You're talking about that nice little curve and what is energy is released or is it absorbed as you travel over. Again, rate affects how quickly you get to where you want to go. Thermo is where do you end up in relation to energy. So by default, it leaves A. But that's exactly how a catalyst works. It gives an alternate route that's less energy that your reaction can proceed via. Questions? Anyone? Do you guys need me to slow down? Do you guys need me to pick up the pace? Is it okay if I go home? Yes? Energies. Just the word energy should start getting you into thermodynamic, not rate. And this is not 100% of the time. This is amazing things that you could correlate. I don't like to say 100% of the time because then there'll be that one problem and then someone comes back like, you were wrong. And I'm like, I graduated. And also the fact that this, just saying mechanism, actually no, let's not go with that. Let's just stay with the energy part. Energy part, thermo, equilibria, not rate. Unless it's activation energy. That's rate. All right. The decomposition of hydrogen peroxide in the presence of iodide ion is believed to occur via the following mechanism. In this mechanism, all right, so a good way to do elimination on this one is going to be, there you have two problems that are talking about the overall reaction and I being present. Add your reaction together. Once you add it, you'll notice that I is nowhere to be found. Therefore, it's neither in the product nor the reactant. You've eliminated B and D as a possible answer. That leaves you just with A and C left. The activated complex, if I'm not mistaken, is when you're doing your energy curve, you add energy, you take the hump of your activation energy, and you reach your transition state, or your activated thing. I mean, that's what I assumed it was to be. And then you drop down to make your products. So again, that's back to thermo. But in case you didn't, we are going to define how to determine an intermediate versus a catalyst. So intermediates are made in one step and used in any subsequent step after it was made. So if you see it made once and then used in the next step, you have an intermediate. And neither of them appear in your overall reaction, first and foremost. And a catalyst is a reactant in the first step and a product in the final step. Questions? So iodine, you can look back at this reaction and see that it is a reactant in the first step and a product in the final step. So it's a catalyst. IO is a product in one step and it's used up in a subsequent step. It is an intermediate. Questions? I'm sorry, what? Yeah. Are we good? Yes? You still want it? Or? All right, so that concludes this chapter. And I'm going kind of fast, but we'll live. Any questions on this chapter? Any conceptual questions? Anything that's been bothering you the whole semester? And you're just like, I have to ask it now. How to solve a logarithmic function? I'm just kidding, don't ask that. Yes? R. Look at the units. There's one R that has atmospheres in it. So if you're talking about atmospheres, you're going to be using that. And the other R doesn't have atmospheres, it has joules. So one is for like pressure and your ideal gas law like stuff, and one of them is for energy. So it depends on whether you're talking about energetics or you're talking about pressure and stuff like that. So just look at the units and then you'll see which R you're supposed to use. Any other questions? All right, cool. All right, now we're going to get to my favorite chapter ever, Equilibria. Boom. I think I have this out of, oh wait, no I don't. All right, so carbon monoxide gas reacts with hydrogen gas at elevated temperatures to form methanol according to the equation below. When 0.4 moles of carbon monoxide and 0.3 moles of hydrogen gas are allowed to reach equilibria in a 1 liter container, 0.06 moles of CH3OH are formed. What is the value of Kc? So the first thing I'm going to do is write my Kc expression. So Kc is products over reactants. And for Kc and all K values, you have to be at equilibria to plug in any numbers into this expression. If you are not in equilibria, and you know that you're equilibria because it says, this is my equilibria constant, if it does not say, concentration, not constant. If the problem does not say, this is the concentration at equilibria, you cannot assume that you're at equilibria, or that any of the concentrations given are at equilibria. So in order to find any concentrations at equilibria, you're going to do an ice table. And the reason why I'm saying this is because it also transfers into pH, also transfers into KSP, and transfers into any one where you're using that K products over reactants. You're going to use an ice table to solve for it. Except in once you get to KSP, then it becomes solubility as opposed to just your X value, which is weird, but that's not the point. All right, so plug it in, onward, and solve. Now we're going to need to solve for this X at equilibria. There are two ways to solve for X. Either your K is given, and you're going to use a quadratic equation, or they give you a concentration of one of them at equilibria. In this case, they gave us a concentration of CH3OH. So we know that our X, since it's up here, and it was given, and they told us that this concentration equaled 0.060, then it was really easy to solve for X. Now you can plug this X back into all the other ones and get all your equilibria concentrations, and you can plug it back into Kc to get your Kc concentration. Questions, comments, concerns? Yes? I would just do small. The best way that I always tell people to neglect X. Look at your KSP, because your KSP is basically telling you how forward this reaction is going. So if you're making a lot of the products and you're going very forward, you're going to have a really big KSP. If your reaction is barely proceeding and you're making no products, then you're going to have a really small KSP. The smaller your KSP, the less that your reactants are affected by the reaction proceeding. So if you have an initial concentration that has like 1 molar, for example, and your K or your KSP or your KQ or your Ka or your Kb is times 10 to the negative 6, negative 5, that's a very small KSP compared to an initial concentration. For me, it's trial and error. I know from gut feeling whether I can neglect it or not. I would honestly say just neglect it for time and purposes. You're more than likely going to get it right. Or close enough, unless they give you like weird pHs, like 8.83, 8.84, oh, great. They're all close to each other. Or weird, that would be for pH only. How would it be for Yeah, that's only for pH that you neglect X anyway, so I'm not stuck. So yeah, if they give you like weird, like they're really close to each other, but if they're far off, neglect it. Go with it, get the answer you get closest to. Now if you're like in the middle between like up and down, then go back and not neglect it. But I doubt they're gonna put a problem like that, just because the amount of time that you have to complete it, you're supposed to be already short on time, right? Like how many questions is it in 50 in 3 hours? Is it really 50? Okay. That's not that bad. You got like a minute. Full disclosure there. All right, any other questions before I proceed? None? Okay. The value of the equilibrium constant can be used to predict each of the following except direction of a reaction, extent of a reaction, quantity of reactants remaining at equilibria, the time required to reach equilibria. What do you guys think the answer is, just by what I've been stressing? Yeah, it's going to be time. Your time can change. You can add a catalyst. You can be at conditions that slow down your reaction. At the end, even if you slow it or speed it up, you should end up at the same place. So the answer is D. Is someone like checking my answers? Okay. Just to make sure that I'm not like getting everything wrong. Here I am like, all of these things, and you guys just leave like, oh, I'm gonna be so awesome. And just you fail everything. It's a horrible thing. Everyone emails the supervisor, your Chem 2 tutors suck. My answer, I graduated. I'm sorry. Chemical equilibrium is the result of A, formation of the products equals, I'm not sure what that's supposed to say. Okay, equal in mass. Okay, perfect, thank you. All right, and B is the unavailability of further reactant. C, a stoppage of further reaction. D, opposing reactions attain equal speeds. So this is where I said that it's not 100% of the time. Rate and everything in chemistry is interchangeable. However, most of the time when they're talking about rate, you're not going to want to correlate rate and equilibria. But at this point is the one time when it is exactly because of that. Your forward rate and your reverse rate are equal to each other, and they're negating each other, so your overall change in concentration isn't being affected. And so the reason why I picked this one is because of A. A is going to be a pitfall for a lot of people. However, if you look back at and think about all the problems you've done, how often are your products equal to your reactants once you solve for K? Almost never. So even though everyone wants to think equilibria, equal, my products and reactants are equal in concentration, that is not the case. So that's why I picked this one it's why I picked this problem, because that's a common pitfall for people. The unavailability of further reactant, that's just your reaction sort of ends, but you still reach equilibria. You reach the equilibria of your limiting reagent. That doesn't affect. That doesn't define equilibria. You still reach equilibria. It's just now depending on the limiting reagent. And a stoppage of further reaction, your reactions don't really end. When you reach equilibria is the end, and equilibria is just you're going forward and backwards. You're making your products and your reactants at equal concentrations. So to amend my question, unless directly talking about the forward and reverse rate when in equilibria, which this also works when you're talking about, they give you your individual mechanisms and rate mechanism, and they said predict the overall rate law, but your second step was a slow step. And so you have to go back to the first step and set your rates equal to each other and solve for it. Do you guys remember this? No? All right, cool. All right, so consider the gas phase reaction. Which reaction characteristic will be affected by a change in temperature? All right, so the first one is the value of the equilibrium constant. And the next one is your equilibrium concentration. Well, by default, if you affect your equilibrium concentration, you affect your equilibrium constant. You can't have one without the other. So by default, like if one's correct, they're either are both correct or are both wrong. You cannot have one without the other. So I can eliminate A and B off the bat. Does that make sense why I took those out? Does anyone need me to repeat that? I will, just in case there's those quiet people. If you change your equilibrium concentration, then you change your Kc, because your equilibrium concentrations are the ones you plug back into Kc. So if if your equilibrium concentrations don't change, then you don't change your Kc. And if they do change, then you do change your Kc. All right, so at this point, we're going to use Le Chatelier's principle to explain and get to the rest of the answer. This is positive, which means that I require energy, and heat is on this side of the reaction. If I raise the temperature, I'm going to drive my reaction in this direction without ever having to add any more concentration. Does that make sense? You never added anything else, but I pushed my reaction to make more products. So I changed my equilibrium concentration, I increased my products and decreased my reactants. And by thus far, since I changed the equilibrium position, I changed my equilibria constant. Now don't get confused with when you add a product or a reactant to it. Because when you're adding a product to a reactant, equilibria shifts so you can get back to equilibria. But you already added something to it. Heat is not a concentration. So heat isn't adding more reactants to it, and then some of those reactants are going towards a product so that you can go back to equilibria. Heat is pushing and changing your equilibria without adding any more products, just pushing the ones you already have in another direction. Does that make sense? So the answer ends up being both of them. All right, consider the reaction carried out at a constant temperature and volume. How can the position of equilibrium for this reaction be shifted to the right? All right, so immediately, which one can I eliminate? I heard everyone say A. Yes, A isn't going to affect a catalyst doesn't affect my equilibrium constant or my equilibrium concentrations. It just helps me get there faster. For this reaction, okay, it wants to shift to the right. All right, so at this point, we're also going to, I'm going to need your help when it comes to how pressure affects and pressure as it comes to Le Chatelier's principle, because I always forget that. So let's work with the concentration ones first. Maybe we'll get the answer there, because I always forget my pressure law, so hopefully either both of these will be wrong, and then by default, it's the pressure one, or one of these will be right, and I judge my balance. So the way that I do these is imagine that my pen is a nice little like seesaw, I guess. So it can tilt down and forward. And there's a ball on it, and gravity's pushing towards me, so towards the bottom of the paper. If I increase my products, you make that ledge go down, your ball's going to roll to the right. Yeah. So if I increase my reactants, my ball's going to roll to the left. And I've been doing this for 4 years now. So removal of Cl2 is going to cause it to go to the right. I found my answer. So I decrease the concentration of Cl2, it shifts to the right, and I have an answer. I can double check with my removal of PCl5. If I remove it, I decrease the concentration, it's going to shift to the left. I know that's not it. I'm actually not sure about the gas because I always forget that law, but I was lucky. In which case, but let's go over it anyway. If you add an inert gas, you're going to increase the pressure. So when it comes to pressure, does it go towards less moles or more moles? Towards more moles? All right, so an increase of pressure is going to go to more moles. It's going to, are you sure you have that one memorized right? Because I'm pretty positive the answer is B. The fact it's an inert gas doesn't affect the overall reaction, but it is going to increase the pressure. You increase the number of moles, you increase the pressure, right? As far as I'm concerned. but it still increases the pressure. It could be that. Okay, we'll just go with that then. Either way, I still got to my answer. And if I was able to cancel out the other two, then by default, it would have been that one. And that's the way I would have tackled this problem because I don't remember the pressure laws. So. All right, questions? All right, so at 0 degrees Celsius, the ion product, so your Kw of water is 1.2 times 10 to the negative 15. The pH of pure water at this temperature is snap. Oh, is. That's what you're finding. Okay. Is question mark. All right, so at this point, we know that our Kw is equal to the amount of hydrogen ions multiplied by the amount of hydroxide ion. Hydronium and hydroxide ions. And the fact that it's pure water is telling you that they're equal to each other. And since pH, and they're asking me for pH, I'm going to keep the hydrogen ion. I'm going to just substitute another hydrogen ion for my hydroxide ion, plug it into the Kw, plug in the Kw that they gave me, and that's going to take the square root. That's going to give me my H+. Follow it all the way down. Once you find your H+ concentration, plug it into pH, solve for pH, 7.46. Questions? Yeah. All right. In a 0.5 molar solution of a weak acid, your hydrogen ion concentration is 1.8 times 10 to the negative 3. What is the Ka? All right, so if you're given, actually this is for any acid. And if you forget the structure, don't freak out. If it says acid in the name, use the general acid equation. Don't be like, I don't know what this is. So we have our overall general acid equation. I've always liked to use the dissociation one, so HA goes to H+ and A-, but that really confused a lot of people. And so I was forced to use the one where it reacts with water, which is a true equation. All right, so your Ka is equal to your products over reactants. Again, in order to find the only concentrations I can plug into Ka are equilibrium concentrations. So to find equilibrium concentrations, you're going to use the ice table. To find X, in this case, they gave us the hydrogen ion concentration, so we can plug in the hydrogen ion concentration for the hydrogen ion concentration, which is equal to X. So it tells us that. We can solve and find the concentrations of all the other ones at equilibria, having solved for X. And then we can plug that back into our Ka, and we get 6.7 times 10 to the negative 5. All right, last and final question. So a 0.15 solution of a weak acid is found to ionize by 1.3%. What is the Ka? All right, if you ionize by 1.3%, that is how much of your original product broke down. And since it's a 1-to-1 ratio, whatever amount broke down is the amount of hydrogen ion that I made. So I'm going to calculate how much broke down. So 0.013 is my percentage in decimal, and I multiply it by my original concentration to find out how much of it broke down. Again, since they asked me for my Ka, to find the Ka, I need equilibrium concentrations. In order to find equilibrium concentrations, I need to make an ice table. And if you guys have been noticing a trend, it's that when it comes to the Ka of an acid or a base, actually let's finish this problem and I'll get to that. So then my X is equals 0.00195, plug it all back in and get my Ka. When it comes to an acid or a base, since you can only do one step at a time, you can only lose one proton at a time, your ice table ends up giving you the same overall equation for Ka. So your Ka is equal to X over your original concentration, x squared, over your original concentration, which is F, so your initial concentration, minus x, where x is equal to your H plus concentration. When it comes to Kb, you get the same thing. So Kb is equal to x squared over F minus x, where x is equal to your OH concentration. So you don't have to do an ice table every time. Every time you do an ice table, you will get to this equation. You could just skip it. It is not the same for, that only stands for pH, because pH you only break one at a time, and you only do one step. All right, any other questions? I'm sorry, come again? F is initial concentration. You can put I just picked F, I don't know why. I think I saw it in a book one time. So your initial concentration of your whatever you added, so whatever acid or base you originally added. Can I go back to 20? Is this 20? Yeah, this is 20. Any other questions? Yes? Is it Chem 1? Let me see if I can do it first. Can I write in this with pencil? Do they give me anything else? They just give me face under it? There's an equation for this already. That relates directly the edge length and the, I don't know the equation, but there's an equation that directly correlates edge length to R. Yeah, so I'm sorry. I don't know that equation by heart. But you can just Google it as well. And when you get me that equation, we can finish that problem. All right, any other questions? I'm obligated by contract to be here till 10:30. So if I'm pretty much done. If I have no questions, we're just going to sit here and stare at each other, yes? You have to memorize it. If you memorize your strong acids, and if it's not a strong acid, it's a weak acid. Same thing for bases. You memorize your strong bases. If it's not a strong base, it's a weak base. If you have no idea what it is, I've never seen this compound, nothing in the name says acid, even though typically, also, if they give you the chemical formula, typically anything with an H in front is an acid. So that's if they give you the chemical formula. And if by, I have never seen this, if it says acid in it, it's an acid. If it says base, it's a base. But if you get this weird thing and I've never seen this before, if they give you a Ka, just go with it being an acid. If they give you a Kb, just go with it being a base. Chances are that that's what's going to be. Or if they give you the Ka, you can find if your Ka is bigger than your Kb, so you can solve for your Kb. If your Ka is bigger than a Kb, then you're acid. If your Kb is bigger than a Ka, then you're a base. So, little ways and if they don't give you a Ka and you have you only have 25% of getting it right. 25% chance. Good? All right, so this is number 23. Oh, sorry. All right, yeah, I'm gonna do number 23 because it's just a lot shorter for me to read. All right, so when it comes to dissolving anything in the big thing about KSP in terms of equilibria, and I forgot to mention this before, it's actually a really big thing when it comes to equilibria. The only thing that matters in your K constant for equilibria are liquids, aqueous solutions and gases. Pure liquids and solids are not included in your equilibria expression. So when you make your ice table, even though you start with this, all you care about is your end product. So, and your solubility, by definition, is how much of it, so you start off with X compound. I don't care how much I start with because it's not going to go into my KSP equation. My KSP equation is only going to equal, why do you guys let me go on with an unbalanced equation? Come on, people. Wake up. All right, your KSP is only going to matter. Your products are the only ones that are going to matter. F minus squared. So if we're trying to find the KSP, I need to find the concentrations at equilibria. My concentrations at equilibria, I make an ice table. And they typically don't do an ice table in the book. I still work off of an ice table. This guy originally starts at 0. I don't care what this, actually, well, this guy decreases, and you have an end concentration of this guy and an end concentration of those guys, which we're going to solve with the solubility. The solubility is how much of my salt dissolves. Well, since this is a 1-to-1, or it's not a 1-to-1 ratio, but when this guy dissolves, whatever amount of this guy that dissolves, I don't want to make that, let's just make that A. I'm going to increase the concentration of that guy by the exact amount that it dissolved, and this guy's going to increase by twice the amount of it having dissolved. So at end, my solubility equals my X, and that's why they make this S and that S. So you can plug in your solubility as your X, do your normal ice tables, and whatever they gave you as a solubility constant equals your X. Plug those back in, solve for each of these at equilibria, and plug them back into your KSP equation. Does that make sense? Because I know that I tackle solubility a little bit different from the book. All right, so when I made the ice table, I made it as it normally does. You start with an initial concentration A, and this decreases by a certain factor, and your end product is A minus X. I plugged in all these variables because that's a solid, and at the end, it's not even going to be included. So I don't really care what the value of A is. I don't care what its beginning product is, and I don't care what its end product is. What I do care is the ions that it makes in solution, because those are going to be aqueous. Solubility, the definition of solubility is how much of my salt dissolves. So if 1 molecule out of 5, so 1 in 5 dissolve, well then that means I'm going to have however much dissolved of MgF2, I'm going to make that amount of Mg because that's stoichiometry, and I'm going to make twice that amount of F because that's also stoichiometry. So you solve it like you would an ice table, except solubility is now equal to X. Plug in your solubility as your X, solve for everything, onward. Yes. You still multiply by 2 and then you square it, yep. You do both. Well, that's mine. Solve it, make sure you get the right answer. Come back to me if you get stuck. Did you hear me? Oh, stuck, yeah. So go all the way through it, solve it, make sure you get the right answer, and if you're stuck, show me your work. Because if you get stuck and I can't read your work, then I don't know what you're doing. Any other questions? Concept questions? We still have 30 minutes. Another question? Mm-hmm.
It's about the
Mm. All right, so when it comes to plating, plating is strictly stoichiometry all the way through. What time to plate 2.0 grams of copper at a constant flow of... All right, when you plate copper, you're adding ions to it so that it can get to its solid form. So you're using the overall equation of copper 2 plus 2 electrons. Let's just use that equation for now, because I don't know what equation you actually use. But let's just assume it's copper Cu plus 2 electrons goes to copper solid. And that's how you plate. Well, they're giving you the constant flow in Armstrongs. There's a way, and I think you use Coulomb's law or Coulomb's number, whatever that is, that's going to convert between Armstrongs to number of electrons, or number of electrons per mole, or that conversion factor. Once you use that, or number of electrons that flow per second. So once you convert Armstrong, it's already number of electrons per second, right? That's my... What are my units of Armstrongs? And what are my units of Faraday's constant? Because I know you use one or the other to get to the moles of electron. Once you get to the moles of electron, then you can figure that out. So first, the first step is getting to number of electrons per second. That's the part where I am confused. I think you use Faraday's constant. Work with your units to cancel out your amperes so that you can get electrons per second, unless amperes is already electrons per second. In which case you multiply by the time to get your number of electrons. And then once you get your number of electrons, you're going to use stoichiometry, which is, sorry, that's 2 electrons. You guys seriously just let me leave all these unbalanced equations. You use stoichiometry, so whatever number you get for your number of electrons that pass with the certain amount of time, you're going to multiply that with 2 electrons for every copper, and you'll find out how many moles of copper. Once you find that, you can use the mass of copper to get to grams of copper. Does that make sense? I'm sorry, what? The time is once you have to get that amperes to a unit of electrons per second, or flow, which is usually current. That's the tricky part. I'm forgetting the actual equation. 13? So this is the one where they tell you amperes, as you can see it there, and you're going to get to seconds. Is my phone ringing? That's not my phone. Okay, so here's where we have 5.5 amperes is coulombs per second, and 1 mole electrons to that. Once you use Coulomb's law to get your top part to cancel out your C's, or use this guy, Faraday's constant, sorry, to cancel out C, so that you eventually end up with moles of electrons. The whole problem. All right, so for this one, what you're going to do is you have your overall amperes given, which is 2.6. Coulombs per second. So it's 1.26 coulombs per second. At that point, I'm going to use Faraday's constant, so 9645485, whatever it is, which will get me to electrons per second. Wait, what? Yeah, no, I can't do this one. I cave. Yeah?
For this one, I used coulombs per second, and then just found coulombs and divided by to get moles of electron.
Oh, wait, it's okay, that's right. I had my units off, thank you. So once at this one, you multiply by Faraday's constant, it's going to cancel out. It's already over 1, so it doesn't really do anything. It's going to cancel out the coulomb, so you're going to be at electrons, and you're going to be at mole of electrons. Once you get to mole of electrons, you use the fact that this guy, 2 moles, you cancel out, you go forward. Sorry. Once you multiply by Faraday's constant, it should get you to moles of electrons. Once you get to moles of electrons, you can do stoichiometry to find your overall copper. Does that make sense? No? Any other questions that aren't on redox reactions, clearly? Sorry. Oh, for the rest of you that are here, if you guys don't mind filling out a review, you can say, be honest, I'm not going to read this. No, actually, I'm really not going to read this. And you can pass them back to me. It's an overall on the effectiveness of study union. I'm not sure if they ask questions about me. They might not. It's supposed to be on the overall effect and quality of what you've had with study union. And what do you mean by number? Snap. Thank you. It's probably, they didn't give me a number. No one told me my number. 53. I'm 53, guys. That is me. So you bubbled in 5 and 3. Like I said, I'm also obligated to be here for the entire time. I'm also obligated to keep my mic. If you're working on your own things and you get stuck, so long as you show me work, most of the time I can get through it. And I can tell you if you're doing bad math or not. 53. For a second there, when you asked that, I thought like you wanted my number, and I'm like, why the hell do you want my number? I'm like, no, you can't call me at 12 o'clock at night. All right, any other questions? What time is it? If you, if, all right, you have to get me the equation, the Claes-Capricorn equation. Write it down for me because I don't know that by memory. But just the fact that it's already correlating temperature and pressure, I already knew. And they were giving me 2 temperatures and 2 pressures, I already knew that that's the equation I had to use. Do they give me a ratio of some sort? I already gave you one. Does anyone over here, do you guys over here need them? I'll be right back. I'll be there in like 2 seconds. How many people do you guys think were here? Like what, 100? And you are left. Thank you. Thanks. I try. That's not a good thing. Still have to take your final even if you die. Give me a sec, like when I'm not up here under pressure, we'll revisit this problem. Just come to me afterward. Burn them all. I'm just kidding. I do want these back. Thank you. What? I didn't meet your expectation. I'm just kidding. What is wrong with you? I'm just kidding. I thought these were anonymous. Not when you hand them directly to me. I read them on the spot. Oh, are you waiting for me? Any other questions? Oh, actually, there's one thing I want to say about redox reactions. On a last note, if they ask you which one's being oxidized and which one's being reduced, or some sort of question, automatically eliminate all of the products. For redox reaction, if they're asking you which one of these is a reducing agent or an oxidizing agent, or which one's being oxidized or being reduced, that is only speaking about the reactants. So if they give you products, eliminate them off the bat. By that chance, maybe you'll have just one left over and you're like, sweet. And at that point, you'll be able to get that. So for you last stragglers, you got one up on everybody else.